So, welcome to our third podcast, and today I'm going to talk about a very interesting research published by Microsoft Research Lab. And this research mostly talks about how people can use artificial intelligence in atmospheric forecasting. What I like about this particular research is that if you look at how weather forecasting or air pollution forecasting is done today, is done using statistical methods or numerical forecasting. And while these methods are amazing, this has been functioning for quite some time. The challenge with these existing methods is that they don't take the vast amount of data that is available for them to consider and have a more context in predicting the or forecasting a task that has been given to them. The second thing is that these existing methods are also computationally intensive. It takes a lot of compute power, and hopefully with AI we can try to do both things together, and that's what this particular research finding demonstrates. I'll quickly go into a jump of it what this model is. In a very simple term, what Aurora Foundation model does, it is trained on diverse atmospheric data such as ER5, CMP6, CAMS, and other data available, and it has created a generalized understanding of what an atmospheric model should look like. Correct? So, very, very powerful thing. And then you can take this foundation model and train it for specific tasks for your area of interest. Maybe you're looking for a particular dimension of weather forecasting. Maybe you're looking for predicting a weather in region where data is not available. Correct? All of those things is now possible with Aurora, or at least it has a potential to do things. And that's what I really like about this research out of it. At architecture level, it is using a swim-based transformer model. Without going much into detail, swim-based transformers are basically, they're a little bit more efficient than the traditional transformers model we have. It has a sliding window approach where it doesn't really look at the entire patch of an image and try to learn about it, but it kind of creates a small segments and then learns iteratively or on a small bits of it. So it breaks down into small pieces out of it. And because it breaks down, it creates a bit of a hierarchy, which allows applications like weather forecasting to be able to kind of a bit more efficient and accurate about it. So at the heart of it, it has encoder and decoder. What encoder does, it basically takes an input and creates a 3D representation of a atmospheric matrix there. And then you use an optimization technique. So LoRa here is a low rank adaptation technique. In this, you don't have to, when you update your weights, when you train your model out of it, instead of looking the entire thing, it only focuses on a small matrix that is specific to your task. And then it creates an output of it, and then a decoder takes that output and gives you the result on it. Phenomenally impressive, if you ask me from my perspective. It has shown that our current methods that we have, it can perform 74% better on air quality predictions and almost 92% better on the weather predictions. And this I'm talking about for air quality, a 5-day air quality prediction index. And for weather, it basically has a high resolution with 0.1 dimension or 0.1 resolution for at least 10 days. So this is super interesting. It's certainly worth considering it from my perspective, given there are interesting geographical changes we are witnessing. You can look at something which is happening in the United States. A few weeks back, it was devastating to see how the chaos that happened in Florida was really disturbing. Few weeks back, Nepal, which is just closer to India, had really devastating floods, and we believe that with help of technology we could be more prepared in addressing some of those issues there. The thing I want to highlight, this is not perfect, so I don't want to put all your hopes into it yet. It's a nice discovery, but it still has its limitation, correct? So what are the limitations that we are talking about? The one thing I want to highlight here is that this is a deterministic model. What do I mean by that is that a deterministic model basically gives you a one specific forecasting output, correct? So let's say if you're looking for weather prediction or temperature prediction, it'll give you 30 centigrade or 45 centigrade, hopefully not. But in real world, weather doesn't function like that. It is not about one particular number, correct? You need a bit of a range, you need a bit of room to play around with that, because if you plan everything just based on one output, and if it doesn't really, it's not successful, then there's a lot of kind of task that depends on it, you have to do again and again. So I strongly feel that a next version of this model should have some bit of probabilistic approach into it, so that you don't just get a one number or one forecast, you get a range out of it, and you can play around with this range and try to do multiple things out of it. I also like the model does a fantastic work in terms of also adapting dynamic data, correct? So sometimes, let's say, if you look at traditional models, they are very fixed and rigid, correct? If you get some forecasting and now you want to kind of change that forecasting, you have to start from all over again. But Aurora kind of demonstrated that it adapts on dynamic data also significantly well. So that was kind of really interesting for me to see that. And also at much lesser computation time, correct? It doesn't use that much of resources that traditional methods are using. So I encourage all of you to read this paper and get a bit more understanding about how AI research is pushing the boundaries in the field of sciences. Microsoft is also kind enough to share a lot of other information, like there are a bunch of examples that you could play around with different data sets. There is an API available that you could integrate in your demo or in your applications and play around with it. And I highly encourage people to go and check this out. So great discovery, very first model, lot of potential, and hoping that it will kind of change the landscape of forecasting with the help of artificial intelligence.
This is amazing. Dushyant, I have a question. In terms of, like, you highlighted how Aurora is based on certain specificities of how the model is built, and that's what makes some of these predictions better, more accurate, and so on. To your mind, do you see different other applications that you could extend this modeling to?
So right now, so this is a foundation. So generally, the concept of foundation model is that it is trained on diversity of the data, correct? Without a specific goal in mind. You basically put that. I mean, you do have a goal in mind, but not a specific, fine-tuned or precise task that you have in mind there. And to my mind, that is a super interesting, because many times people do not have that much of data required to be trained a model to get that efficacy performance out of it. It's like somebody is coming and building a foundation for you, and then you can build a house or any monument on top of it. So I think that's how I look at it. Beyond forecasting, I'm just trying to see where the application of this model could be. Flood forecasting could be one such thing, but again, it would need that additional piece of data to be able to kind of create that. So flood forecasting, weather prediction, and air quality and weather predictions are by out of the box. The model does, but you can take this and do flood forecasting. You can take and I think in some of the other discussion we were talking about, can we look at landslides? Correct. That is another interesting area to that. But for that, you need another set of data combined with Aurora and how you can predict. So I think the opportunity, if you ask me, is massive. If you have the data, we should definitely go about it.
Limited only by imagination and data sets.
Yes.
No, that's pretty cool.
Yeah, I think what Dushyant you've just mentioned, right? Like people don't have access to data, right? And I think foundational models are so helpful, right? Like when we were building, one of our products, we didn't have access to data, right? And no publicly available data could exactly match our use cases, right? So that's where data created or leveraging some of these foundational models were absolutely critical, right? Now we have a fully working workflow, right? And we've created our own model based on the data plus, that we've kind of leveraged foundational models like this were absolutely critical. Like, we couldn't build our own models if it wasn't for this, right? So I think we have so many researchers, right, on climate. How do they kind of leverage this, right? How's that gap of them understanding that this is something amazing? I think that realization has probably not happened. And second, how do they actually practically use this? If there was a way to bridge that gap, I think we'd see so many interesting research papers or models or smaller use cases, right, in different parts, because you're no longer bounded by data.
So as I said, this is a very early iteration. There's a lot of scope of improvement, both in terms of performance, adaptation, efficiency. But even if people want to use this model today, it doesn't hurt. Imagine, let's say, if somebody in India who has a data for last 5 years about air quality index or about weather prediction, correct? And you don't, if you have a 5 years, fantastic. But if you don't have 5 years, maybe you have a little bit of a small data. Can I take this model, which I just showed you, it is available on GitHub, people can just create their own infra and run this particular model and train it with that specific data for India, and can get information about what could be the air quality index going to be look like in Diwali in Delhi, which in my view would be a very interesting problem to solve, and how good it is. And once you have that information, that okay, imagine, so right now it gives you a deterministic point which is a particular number, but if you have a range, then you can plan things accordingly. Other thing, you can actually zoom down. So in weather prediction, you can, as I mentioned, you can go to 0.1 resolution and find out which areas are going to get impacted. I strongly believe that AI is a field where we will learn more by sharing and by keeping learning with ourselves. Now, be it modeling, be it architectures, weights, data. Of course, take necessary steps. We don't need to kind of cross the boundary there. But if there is a possibility in terms of driving or advancing the field of AI by doing any of those things, I would recommend that.